Assalamu alaikum. Welcome to lecture 10 of data mining. Today we will start discussing another scalable algorithm for frequent item set mining, which is known by the name of frequent pattern growth algorithm or FP growth algorithm. Uh, Previously, we had discussed the a priori algorithm, which was the first scalable algorithm for finding frequent item sets in transactional databases. We also discussed some extensions and tweaks that can be done to the basic a priori algorithm to improve its performance. Uh, so we talked about a number of ways to improve its performance. I think one of those ways is still missing. We'll start with that today, and then we'll move on to the FP growth algorithm, which is the most popular algorithm that is used in practice nowadays. So today at the end of class, you also have a quiz around 1:35. And in addition to that, I have already confirmed the date for the midterm exam. The midterm exam for you guys is on March 4, which is a Friday at 6:30 p.m. So 6:30 to 8:30, 2-hour slot for the midterm exam. So the midterm exam would be on campus in room 201. You can bring a help sheet. Help sheet can be double-sided, and you can write anything on the help sheet, but it should be just one page. And of course, you need to bring a calculator and anything else for writing. So I will send out the syllabus for the midterm later on, but of course, it will contain all content that we have covered till next Tuesday. So, and the format would be similar to some of the midterms exam that are taken before, with two sections. The first section with shorter questions, the second section with longer questions. All right. So are there any questions? The long questions would typically involve some application of an algorithm. So you will be given some small data, and you will be asked to apply some techniques that we have studied in this course so far. So for example, you might be asked to, for example, the a priori algorithm or the FP growth algorithm or some of the techniques that we talked about in data preprocessing. All right. So So last time we were discussing some extensions and tweaks that can be done to the basic a priori algorithm. We talked about the partitioned a priori algorithm. We talked about sampling approaches to a priori algorithm. We also talked about tagging transactions that do not contain a particular item set so that they are not uh, scanned in the next scan of the database, which is often known as the dynamic item sort counting technique. And then finally, there is one technique or class of techniques which is based on hashing. So, and hashing basically candidates. So, as we mentioned last time in the a priori algorithm, the number of candidates that are generated can become very large even after pruning. And this typically happens for most practical applications for candidate 2 and candidate 3. So why they occur for C2 and C3? Because at that point, a large number of item sets have not been pruned, and once you join the self join process, you get a lot of uh, candidates. And of course, lots of candidates will require lots of memory and then processing them by scanning the database and counting them. So that's a lot of overhead. So you can reduce some of this bookkeeping by using the simple hash data structure or hashing approach. The idea here is that it's very simple. We'll discuss the ideas. We won't go into the details of the various techniques because there might be slight variations. We'll discuss the idea. So all of you must be familiar with hash tables. Uh, and given anything, you can hash them to specific bins or buckets. So, so let's say we define some number of buckets, let's say k buckets, k bins. Usually k is an odd number, all right? Of course, this is from the theory of hashing. So the idea is that whenever you are doing some C, you have some LK item sets. From this LK, what do? You do LK joins with LK to give you CK or CK plus 1. So that's the standard operation, the level by level growth operation in a priori. And let's take the example of L1 joining L1 to create C2. So what do we have? We have single item, let's say A, B, and C. And from this A, B, C, you can get AB, for example, you can get AC, and you can get BC, for example. So what do you do is whenever you generate the next higher order candidate, you also hash them into bins, and you have to define an appropriate hashing function. So hashing function can be based on the lexicographic order of the item set. For example, one simple way could be, for example, A is the first item, right? So, and first in the lexicographic order, so we can give it a value of 1, right? And since it's in the first position, we also give it a value of 1 for the position. So what happens is we get 1 into 1 plus the second is B, which is second position, into 10. And then, of course, uh, modulo whatever number of bins that you are using. Let's say you're using 5 bins, so mod 5, for example. So this will give you a number. Let's say what this would be: 1 plus 20, 21. 21 mod 5 would be, we get 20. So, which would be 0. And then 21, which will be 1. So you'll get a value of 1. So this will be binned into bin 1. You have a question?
Sir, why are we multiplying by 10?
Uh,
2
we are
समझ आता है कि
defining,
B
we are defining a
B
hash function. No, we are using 2 for B, and we are using 10 for the position. So the first position, like unit, decimal, hundreds, so and so on. So for example, first is unit, we are using 1 there. Second position is 10. Third position would be 100. Fourth position would be 1000, and so on. And then, of course,
sir 51
lexicographical order 1, 2, 3.
51 आर्बिट्रेरी है, कुछ भी हो सकता था.
हाँ, कुछ भी हो सकता है, बट ये हैशिंग फंक्शन के रूल्स अप्लाई होंगे. सो बैड हैशिंग फंक्शन होगा तो आपका हैश अच्छा नहीं होगा. तो दिस इज वन फंक्शन दैट हैज बीन प्रपोज्ड फॉर आइटम सेट्स. ठीक है ना? सो आइटम सेट्स के लिए ये प्रपोज किया गया, दैट हैज बीन यूज्ड, वेयर पोजीशन के लिए आप वो यूनिट, टेंस, हंड्रेड, 10, 1000 यूज करें, और लेक्सिकोग्राफी के लिए यूनिट्स यूज करें 1, 2, 3, 4, 5, 6, and then you multiply them and take the mod with the number of bins. So what happens is that if you do this, so AB gets hashed to bin 1. So let's say bin 1, this goes to AB. Then you also have bin 2, इसमें भी कुछ आ जाएगा. And similarly, bin 3, इसमें भी कुछ होगा. Bin 4 में भी होगा. और bin 5 में भी कुछ होगा. Of course, this is I'm using a very small example. So I'm using a very simple example, but I'm not going to AB का तो मैंने बता दिया किस तरह ये bin 1 में आ रहा है. But let me arbitrarily add other item sets. So let's say इसमें DG भी आ गया, इसमें let's say DM भी आ गया, और इसमें for example दूसरे में AC आ गया, इसमें EF आ गया, and so on. So you will get multiple items for each bin. ठीक है ना? Multiple item sets. So the idea, the basic idea, of course, there are variations and tweaks further. The basic idea is that if for all the item sets in a bin, so if you talk about this bin, इसमें 3 item sets हैं. So if the sum of item sets in all of these bins is less than the minimum support, इसका मतलब है कि each of these item set is also less than the minimum support. So what happens is that at the next step, you drop the entire bin and you do not keep track of any of those items. ठीक है? So for example, जैसे ये जो मैंने कहा है, let's say minimum support count, let's say 10 for example. इन तीनों का sum करके let's say sum 9 आ रहा है. इसका मतलब है कि obviously each one of them is less than 10. ठीक है? So you don't need to do any further processing on this entire bin and you can drop it. ठीक है? You have a question? ठीक है. So this is actually the basic idea. Of course, इसमें variations हैं और वो variations of course come from various papers. तो वो details हम probably discuss नहीं कर सकते इस course में. Otherwise, we'll be spending all the time of this course on this small idea. The idea, as I said, is using a data structure to combine multiple item sets to bins. And of course, in real world problem, there might be thousands of bins, and within each bin there might be hundreds and thousands of item sets. So think of this: if hundreds of thousands of item sets can be dropped at once, so you have significant reduction in space and as well as computational complexity. Okay? So this is the idea of hashing, and in general you can use other data structures as well. For example, the tree data structure is also used for item set counting, so we did not discuss that. And of course, there are other variations as well. So any questions with that, we would like to conclude the a priori algorithm and then move on to the next major algorithm, which is the FP growth algorithm. Okay, so we want to move on to the next scalable algorithm, which is the frequent pattern growth algo, which is simply called FP growth as well. Okay. This algorithm was proposed in 2000 or 2001, and it was proposed by Han and his colleagues. Han is the author of one of your textbook from UIUC. And as I said earlier, FP growth and its variations are now the most commonly used techniques in practice. Of course, I think earlier on it was also patented, तो patent के वजह से भी issue था, but now I think it's quite widely available. So this is the most popularly used, and it's much more efficient than the a priori algorithm. So this algorithm uses a few additional tricks. So remember, a priori also used some ideas and some tricks. So FP growth uses some additional tricks. So I will list those tricks here, and then we will discuss them in slightly bit more detail. So first of all, it basically uses frequency ordering of items in item sets. So if you recall the a priori algorithm, it uses some fixed, what we call the lexicographic ordering of items in item sets. While in the FP growth algorithm, we use a frequency-based ordering. So the most frequent item would be placed at the top of the list, and the next would be placed at the top of the item set, and the next and the next and the next. So frequency ordering, frequency descending order. And the reasoning for this is you can do data compression as a result. And we will discuss the details. And another reason for or using of the data compression is it uses a specific data structure, a tree-based data structure, which it calls the frequent pattern tree for storing item sets. And in this tree, of course, the frequency ordering is utilized. So we'll discuss that as well. So frequency-based ordering of item sets is utilized while entering item sets into this tree. And of course, using the tree, it does further processing. So through the tree, it can compress the data set, the whole set of item sets. And hopefully, if this fits into memory, then you're done. You don't need to do any further scan of the database. Then some other characteristics is this is basically a divide and conquer algorithm. So we have various classes of algorithms from algorithms and data structures. So this is a divide and conquer algorithm. It is also recursive. And secondly, thirdly, it is depth first. Remember, a priori was breadth first, meaning that we did level by level growth, meaning that we first found single items, and then we moved on to 2 items, and then we moved on to 3 items. While in the FP growth, we will, let's say, start with A, and then maybe generate the next one, AD, and then generate the next, basically ADE, let's say, and so on. So depth first. It will complete this path first, and then go back to B, and then go back to C, D, and so on. So this is depth first. So these are some of the ideas that are used in the FP growth algorithm. To understand some of these ideas, let's also discuss database projection. So, and of course, we are talking about transactional databases so far. So let's say we have a transactional database. The first transaction is, let's say, A, B, C. Let's say the second is B, C, D. Let's say the third is B, D. Oops. B, D. And let's say the third is AD, fourth is AD. Okay? So we have 4 transactions. So let's say I want to create a projected database, a projected database. So what does this mean? This means that this would be the partition of the database that contains the item A, or this A could be an item set also, but in this case, it's a single item that contains item A. So if you look at this original transactional database, the first transaction has A, ABC. So there is no A in the second transaction. There is no A in the third transaction. And there is an A in the fourth transaction. So the A projected database would be ABC and AD. Okay. So this is the portion of the database that contained that item or item set. So let me say that A is, let's say, frequent. Just to give an example. So if A is frequent, so in this example, actually, there are no other. So frequent would mean that I don't know what I defined the frequent count. If it is 2, then there are no other single item that are 2, ABC and AD. Okay. So if A was frequent, so any other item set that is frequent in this projected database, so that means that that would also be frequent. So that is one of the reasons for growth. So let's say, let me hypothetically change this example, ABC, ABC, and let's say ABD. Uh, uh, ABC, let me just change this, ABD. All right. So now, so this we know, for example, let's say if we know okay, A is frequent, and then we create the A projected database, which is given here. So if in this projected database, we compute the count of B, for example, so B is also frequent, recurs twice. So from this, we would know for sure that AB is also frequent. So we computed the A projected database, and we already knew A was frequent. In the A projected database, we did the counting again, and we found that B was frequent. So which would then mean that A, B together would also be frequent. So this is the idea behind growth of that is used in FP growth algorithm. Okay? So let's go back to the okay. So let's say again continuing this, let's say if I want to find the AB projected DB. So which transactions would this have? So it will contain the first transaction, which is ABC. So it will not have the second because it does not have A. This would not be this as well. So it will just have one transaction. So it will have just ABC. So the partition that contains that particular item set is returned. So this idea of I think projected database is clear. It uses the same idea in FP growth, but with a slightly different notation. It calls it the conditional pattern base. So instead of writing AB, so AB conditional pattern base would simply be C, because we know for sure that each transaction will also have AB. It just writes the additional item or item set in addition to AB in each transaction. So conditional pattern base. This pattern base is conditioned on the projection item set AB. Okay, so I think you'll get better idea of this use in the FP growth algorithm. So let's go to the FP growth algorithm itself. Okay. Okay, PDF ही है अच्छा फिर खोल लेते हैं so let's look at an example. So minimum support is 30%. First of all, you need to, at least for hand computation, we will need to convert this medium support to minimum support count. Okay. And the table here shows the item sets. And of course, there's an additional column. We'll talk about that later on, which is the ordered items. So there are 8 transactions. So minimum support count by taking 30% of it would be, so 3. So you need to have at least 3 transactions that contain an item set for it to be frequent. Okay. Okay. So how does the algorithm now proceeds? So you have to do one scan of the database at the start, and this step is actually similar to the a priori algorithm. You scan the database and count the counts of all single item sets. In other words, C1 and L1 in a priori. So in this database, we count the counts of all single items. So I've counted all the items that occur, single items that occur in this transactional database. B occurs 6 times. So D also occurs 6 times. A occurs 5 times, and so on. So in this list, in this is basically L1. We have dropped all items that occurred less than 3 times. And that's one thing. Secondly, I have written this in frequency descending order. And of course, whenever there is a tie, I arbitrarily choose one order. So in this case, B6, B को पहले लिख लिया, D को बाद में लिख लिया. उल्टा भी कर सकता था. But again, एक मैंने order fix कर लिया. B पहले, फिर D बाद में, फिर A है, फिर E है, फिर C and so on. ठीक है? And of course, frequency descending order. All right? So now this is done after the first scan. Now, using this F list, we compress this database, which is the database of item sets. Of course, for this F list, we have to order each item set according to this F list. So this order is shown in the rightmost column. So for example, and if any item set is not frequent, वो remove कर दिया हमने. So इसमें जो है ना वो, so we write first D, P, D, then A and E. We write it in that order, even though originally वो किसी और order में लिखा हो सकता है. ठीक है? So now, so we had scanned the database once, found single item sets. We have written them in frequency descending order. And then we scan the database now second time, look at each transaction, write that transaction in frequency descending order and insert it into a tree. And this tree is basically the frequent FP tree, frequent pattern tree. So this tree basically starts from the root null. So meaning that it has a root which is written as null, and from the root you put the transactions in sequence. So maybe I can, yeah. यहाँ आपको फिगर नजर आ रही होगी. Okay. So, okay, so let me. Uh, all right. So, so basically, the tree. So the tree basically starts from a null, and then you enter all the transactions in the frequency descending order. So let's say you have scanned the first transaction. I don't remember the exact transaction. I'm kind of afraid, but let's say B ये 1 है, और let's say A है 1 है, और फिर let's say C है 1. So we enter the first transaction into this, and we get this from the null. We put the entire transaction in frequency descending order. B पहले आया, फिर A आया, फिर E आया. So this is the first transaction. Then we scan the second transaction, or let's say since it is always written in frequency descending order, it is possible that B would be repeated. ठीक है? So B का count आएगा, we start from the null and देखेंगे B पहले ही है, तो B का count हम बढ़ा देंगे 2. और लेट्स से उसके बाद फिर A आ रहा है, तो उसका भी काउंट बढ़ा देंगे 2. एंड लेट्स से उसके बाद कोई और चीज आ रही, E आ रही, तो वहां A से एक ब्रांच निकल जाएगा E के लिए. सो दिस इज द सेकंड ट्रांजेक्शन. लेट्स से थर्ड पे जाते हैं, तो लेट्स उसमें सिर्फ B ही है. अगेन स्टार्टिंग फ्रॉम द रूट, हमने देखा B पहले ही है, 2 था, उसको 3 कर दिया. लेट्स से फोर्थ ट्रांजेक्शन आते हैं, लेट्स से वो स्टार्ट ही A से होता है, तो फ्रॉम रूट से हम A का एक ब्रांच निकाल लेंगे, and we start that. So in this way, you are able to compress all the information in the transactional database. Why are we able to compress? Because we have kind of brought all the frequently occur items on top of the tree, and they are repeatedly used. It's just the counter is increased. Okay. So you are able to now represent the frequent item sets in the transactional database in a more compressed fashion. And people have shown that in practice, for many practical data sets, you can get up to 100%, up to 100 times data compression. So is this clear? Let's see. So as I said, so let's say पहले वो B1 था, B फिर एक और ट्रांजैक्शन में आगे 2 हो जाएगा, फिर कट करके 3 कर देंगे. लेट्स से B के बाद A आ रहा था इधर, A भी फिर 2 दफा आया, B A 2 हो गया. लेट्स से B के बाद D आता था, D1 हो गया. So let's say given J आपके पास FP tree है, what can you say about the transactions in the transactional database? So it means that BA occurs twice, then there is also a BD that occurs once. So इसका मतलब B3 हो गया, BD BA 2 दफा आ रहा है, और BD एक दफा आ रहा है. So B3 हो गया, और B. So if I write the transactional database here, then you will have BA एक है, दूसरा भी BA है, और तीसरा BD है. So it contains all the information in the transactional database. Of course, single items that are not frequent are dropped. Let's say कोई item set F list में नहीं था, तो वो इधर नहीं होगा. But this representation is complete for item set mining, frequent item set mining. All information is contained there. So first scan, we create the F list. Second scan, we create the FP tree. And FP tree, of course, is a compression of the database. Hopefully this FP tree fits in memory. If it fits in memory, then all further processing will be done on this tree. ठीक है. And of course, this is where we go into the divide and conquer recursive approach, where we grow the pattern. So let's look into that step. So I think you can see the tree here, the original tree. I've drawn it here. Okay. So now we do the recursive approach. We start with F list, और जो उसमें सबसे थोड़ा count item set है last से हम शुरू करते हैं. उससे हम projected databases या conditional pattern base बनाने शुरू करेंगे, which means basically means the partitioning of the database. तो database अब tree के form में है, ठीक है. It's not in a standard tabular form, it's a tree के form में, but उसी tree की form में हम सारी transactions निकाल सकते हैं या pattern base निकाल सकते हैं. So now we are trying to find a conditional pattern base for C. So in the tree, look at all nodes that have a C there. Okay? And then backtrack from there. Okay? So that would be the conditional pattern base, because those represent transactions that contain C. Okay? So if I look at into the tree and find those, then I'll find that C. So BDAC occurs once. So actually what happens is BDAC, BDAEC. So BDAEC occurs once, but we do not write C because it is the conditional pattern base for C. Okay? And the count for that, of course, is 1 from the tree, because C us path में 1 आ रहा है. So B, C भी आ रहा है, वो भी once है. C नहीं लिखा इसमें. BAEC भी आ रहा है, वो भी 1 है. ठीक है? So now this is the conditional pattern base for C. C का count 3 था, which is frequent. अब इसके अंदर हमने देखना है कि, by the way, this is another transactional database. Divide and conquer हम का approach कर divide कर दिया हमने. अब इसके ऊपर फिर हम FP tree बना सकते हैं, recursive. इसको फिर compress कर सकते हैं if you want to. So इसका F list बनेगा. अब यहाँ frequent item sets कौन से हैं? B. So B is the only frequent single items, B3. अब इसको फिर हम एक FP tree में डालेंगे. हर ट्रांजैक्शन में देखेंगे, उसको इस एफ लिस्ट की तरह में करेंगे, एंड वी विल गेट ए वेरी सिंपल what happened. इसको आई थिंक आई कांट डिसाइफर, थोड़ा सा गड़बड़ लग रही है मुझे इधर. So actually, since we only found the single item B as frequent, तो इसका simple बनेगा, null से नीचे B3 होगा. ऊपर जो बना हुआ है, I think my screen reader is not reading it properly, कोई issue लग रहा है. So now we started with a conditional pattern base for C, which was count of 3. Then in that conditional pattern base, we found that C is also frequent. B is also frequent with a count of 3, which means that BC would also be frequent with the count of 3. Because C का भी 3 था, B का भी 3 था, BC भी दोनों इकट्ठा 3 दफा आ रहा है. जो भी इसमें मिनिमम वैल्यू होगी वो उसका काउंट होगा. ठीक है. So actually we have done a growth here. And since अब ये जो ट्री आपके पास आया है, इस पे फर्दर आप इस पे रिकर्शन नहीं कर सकते बिकॉज बी का पाथ खत्म हो गया. So you go back to the top list and go to the next item, which would be E. So E का फिर कंडीशनल पैटर्न बेस बनाएंगे. So ये कंडीशनल पैटर्न बेस E का आ गया. इसकी F लिस्ट बन जाएगी. अब इसका FP ट्री बनेगा. यहाँ से सही है ना, ऊपर पता नहीं पढ़ को नहीं रहा था सही. ठीक है. So A4. ठीक है ना. अब यहाँ अब आपके पास एक ट्री आया है विच इज नॉट ए सिंगल पाथ. ठीक है. सो नाउ यू विल हैव टू डू ए रिकर्शन. अब ये A4 था, अब इसके अंदर आप देखना है कि लोएस्ट कौन सा था, उसके ऊपर आपने रिकर्शन करनी है. सो D वाज, पहले हमने E का किया, एंड नाउ इन दिस पार्टीशन वी फाउंड दैट D वाज द लीस्ट फ्रीक्वेंट. उसको डाल के हमने फिर एक और इसको फर्दर डिवाइड किया. And if it ends here, we generate the frequent patterns and we go back again up. मतलब जैसे recursion आप करते हैं ना, you go full depth, go to next up level, वहां से भी recursion पूरी हो जाए, next up level until you go back to the top, then you start again and so on. So in this way, you will be able to grow patterns from single items to larger items up to the maximum length of the item until you cannot do any further growth, and then you go back. ठीक है. सो इस तरह ये प्रोसेस सारा चलेगा. सो इसमें थोड़ा सा आई नो कि एक दफ़ा आप खुद ही इसको जा देखेंगे तो यू गेट ए बेटर आइडिया. मे बी आई विल गिव यू अनदर एग्जांपल बिफोर आई मूव ऑन. सो what is happening here? So let's say we have a FP tree null. Let's say I say that this is a conditional pattern base. Okay, let me take an example for, let's say, E is equal to, let's say, 4. So let's say the conditional pattern base for E is equal to 4 is, let's say, AB is equal to, let's say, 2. And let's say, which means that A, B, D is 2. And let's say A is, let's say, 2 also, that will make it 4. E के साथ है. ठीक है. तो लेट्स से यही सिंपल ले लेते हैं. ठीक है. सो अब ये आपके पास CBB, अब इसकी F लिस्ट बनेगी. A कितनी दफ़ा आ रहा है? A 4 है. B कितनी दफ़ा आ रहा है? 2 आ रहा है. ठीक है. Of course in ordered form. And let's say, for example sake, let's say 2 हमारा minimum support count से कम है, तो we will not write this. ठीक है. And we will be left with A. So इसका मतलब है कि जब हम वापस उन ट्रांजैक्शंस को देखेंगे, वो हमारी ट्रांजैक्शन सिंपली A2 हो जाएगी और A2 हो जाएगी. B नहीं आएगा उसके अंदर. The FP tree, the transactions in the F list form. अब इसको फिर मैं अपने एक ट्री में डाल सकता हूँ if I want to, which simply would be A4. ठीक है. So from this, since this is a single part tree, you don't need any recursion. इसका मतलब ये है कि आपका ग्रोथ हो रहा है, पहले E4 था, आपका ग्रोथ AE4 भी आ जाएगा आपके पास. ठीक है. Because in this projection of E, A is also frequent. So it's with a count of 4, it means that AE is also a pattern of count of 4. So let's say hypothetically, let's say इस projection में A का count 3 आ रहा होता, तो then AE का count जो आना था वो minimum वाला आना था, 3 वाला आना था. Because इस projected database में A का count 3 दफा आ रहा है, so इसका मतलब and हर के साथ of course E आ रहा है, तो then AE would be of count 3. So whenever you get a FP tree with a single path, let's say single path है A, let's say 4 है, C, let's say 2 है. So you can stop the recursion there and generate all the patterns right away. You don't need to do recursion on a single path. But if it has multiple paths, recursions आपको करने पड़ेंगे. So single path से क्यों नहीं करने पड़ेंगे? Because you know all the patterns here. So इसमें patterns कौन से हैं? So क्या था? So A and C थे. So for example, you know, for example, that AC occurs twice, for example, right? And then of course A occurs 2 times. So इनके साथ आप combine, let's say this is a projected database for, let's say, E, तो इनके साथ E लगा के आप इसको grow कर दें. तो आपके पास for example ACE आ जाएगा और फिर of course AE आ जाएगा. ठीक है? इनकी जो काउंट होगी वो मिनिमम वाली होगी. AC का काउंट फॉर एग्जांपल इधर 2 था और E का काउंट लेट्स से ज़्यादा था, तो ये AC का काउंट 2 होगा. सॉरी, AC का काउंट 2 था और लेट्स से E का काउंट 4 था, तो ACE का काउंट 2 रहेगा. एंड लेट्स से इफ यू डोंट हैव अ सिंगल पाथ, जैसे शुरू में भी जो ट्री बना था मल्टीपल पाथ से, उसमें उसके लिए आप रिकर्शन करते रहेंगे आप जब जब तक सिंगल पाथ नहीं आ जाता, एंड until you are able to generate all patterns from there. So it could have multiple paths, for example A4 है इधर और नीचे भी एक पाथ चल रहा है, let's say C, let's say 2. So in this case इसका F list बनेगा और जो भी pattern बनेगा, you might not be able to stop here, you need to do a recursion until you get a single path. So please look at the example. I will upload this example as well. You have example in the book as well, और एक example slide में भी है. So I think without looking at example at your own time, you won't be able to fully understand the FP growth algorithm. So stepwise, it is simply you do a first scan of the database and find all frequent one item sets that is similar to a priori. But you then order that one item set, frequent one item set, in frequency descending order. The second scan of the full database would then insert the transactions in the FP tree using that F list, which is a frequency descending order list. In other words, you're compressing the database. So now you have a compressed database. From the F list, you do recursion now. Starting from the last item, you do projections for that item from the tree, which we call conditional pattern base. You get a new database. ठीक है ना? Projected database is a new database. अब उस database को further tree बना लें उसका, ठीक है, if you want to. And from that tree, if you need to do further projection बन जाएगा, further tree बन जाएगा until you reach the end. Once you have reached the end, you go back and then you do the next depth search. And item sets are generated at each point by concatenating the conditional pattern based item or item set with the items that are frequent in the projected database or in the conditional FP tree. So projected database is the term that I talked about earlier. यहाँ वो conditional pattern based और conditional FP tree की बात करते हैं, ठीक है? ठीक है. So I think I will probably discuss FP growth again a little bit next time. अभी मैं ये नहीं करता because I think सारों के ऊपर से गुजर रहा होगा. So spend some time on looking at the algorithm next time. A couple of other ideas इसमें हैं. I want to give some examples for that, but I will do that next time. So now let me just quickly discuss a final class of algorithms. Again, this will be discussed very briefly, which is the vertical format based item set mining. So far we have talked about transactional databases that were looking like this. So you have the first transaction 1, let's say ABC, transaction 2, let's say BC, and transaction 3, let's say AD. Okay? So this is the normal format of the transactional database. The vertical format flips it or transforms it. What is it is you first find all the single items in your database. And of course, this applies to higher order item sets as well, but वो हम डिस्कस नहीं करेंगे, वो एल्गोरिथम में आप जाएंगे तो आपको पता चलेगा, बट आई वांट टू गिव यू द आइडिया. क्या हुआ है? Just a second. So the single item that we have is A, B, C and D. पहला A, B, C है, दूसरा B, C है, तो तीसरा A, D है, ठीक है ना? So now we flip the database. A, so A किन transactions में आ रहा है? A transaction 1 में आ रहा है and transaction 3 में आ रहा है. B किस transaction में आ रहा है? 1 में आ रहा है, 2 में आ रहा है, right? 3 में नहीं आ रहा. C किस transaction में आ रहा है? 1 में आ रहा है, 2 में आ रहा है. D किस transaction में आ रहा है? 3 में आ रहा है. So this format is called the vertical format. ठीक है? And of course, this vertical format is for single items. Item sets के लिए भी बना सकते हैं, but here we have shown it for single items. What's happening here? ठीक है? So let's say you have this vertical format. So what is now the count of the single item A? So it's simply the number of transactions that appear or number of IDs that appear here, which is 2. ठीक है? 2 transactions में A आ रहा है. What about B? 1 and 2, right? ये भी 2 है. So in other words, in the vertical format, so if you want to find the count of any item, let's say A, it's simply, so, okay, let's say, so A item set, basically you can call this the transaction ID. TID of A is the set 1 and 3. And the TID of the item set or item in this case B is basically 1 and 2. So according to this, then the support count of A is simply the set count of TID of A, ठीक है, which is of course 2. ठीक है. Similarly, if you want to find the transactions that contain A and B, so TID of AB would be simply what? TID of A intersection with TID of B, which essentially is 1. ठीक है. So transaction 1 contains both A, एक second, I think 2 होगा ना शायद. AB तो टाइम भी नहीं आ रहा. ABC, BC, एक सेकंड, क्या था एग्जांपल? A12, तो B3 है. 13, B12, ठीक है. So AB is only 1, ठीक है, सही है. So the first transaction has both A and B, ठीक है, ठीक है. So let's say आपने अब इसका count देखना है. Simply it's the size or count of the elements in this set, which is 1. So this is the main idea behind the vertical format. अब इसमें of course several variations algorithms हैं, fancy names के साथ. Let's say eclat है, एक algorithm है. These algorithms we won't go into the details of that, as we had done for example, a priori and FP growth. But the idea is that they first transform the database into the vertical format and then find or do all operations in terms of sets of transactions. And higher order item sets can simply be computed by taking the intersection of lower order item sets. ठीक है. और इसमें भी आप वो वाला फ्रेमवर्क यूज कर सकते हैं. ए प्रायोरी वाला फ्रेमवर्क भी कर सकते हैं, एफपी ग्रोथ वाला भी कर सकते हैं, बट इन द वर्टिकल फॉर्मेट. Again, these are variations that are used in practice. So I think that is, I think, essentially what I wanted to cover today. इसके बाद I think a couple of things मैं FP growth के discuss करूँगा, and then we'll move on to sequential pattern mining in the next class. Please look into the FP growth algorithm at your own time. I'll upload the examples. There are examples in the book as well as there are also examples on the web. So it's fairly easy, but you need to go through the steps by yourself once. So it's basically a recursive divide and conquer approach. So any questions so far? So I think you still have about 5 minutes before the quiz. So any questions on the content that we covered today, or even the content that we covered in the previous lecture? ठीक है. तो जस्ट टू रिमाइंड अगेन, आपका जो मिड टर्म एग्जाम है वो नेक्स्ट फ्राइडे है at 6:30 ऑन कैंपस इन द एसएससी बिल्डिंग. ठीक है. So most likely हमारा ये last quiz होगा before the exam. So next Thursday, next Tuesday को हो तो सकता है quiz, but maybe we will not have a quiz next Tuesday. And then of course on Friday we have the exam. So no questions. सारे quiz की तैयारी हो रही है.